what level is your, I don't know, like alternatives to least squares? That means like best subset selection, step forward selection, cross validation. What level are you? You are aware? What would you like to know? Have you got any questions already? Would you like to talk something about something in particular, or should I just see the chapter? Just tell me.
I think I understand the first part, and that's something I've covered before in detail, like subset selection and forward and backwards. And then I haven't covered as much slash read the full chapter of the rest of it. So, but I'm really interested in the regularization and ridge and lasso and stuff.
Okay.
I'm more in the Bayesian camp, and I skip these things that resemble p hacking, but sometimes we'll go straight to GlimNet, to lasso and ridge kinds of models. I think I understand the danger of using the stepwise tools, and I don't even bother presenting those to unless somebody very specifically wants to see the difference between two models, but most say business users aren't that sophisticated, and if they were given something that came through GlimNet that biased the predictors on its own, they couldn't argue with that, and so it's been okay just to skip to the second half of the chapter.
Okay. All right. So we go through. We'll see some. I was thinking to do half of the chapter with the lab, and then the other half of the chapter with the lab, without going much into the theory. But as the things are here, we go through the chapter together and see. Okay. So let's say that this chapter, as we know, is about so the main point of this chapter is that so this chapter is based on selecting the number of predictors. And this obviously is when you have a certain high number of predictors, okay? So for selecting these predictors in a way that you can make a model which will be readable and would release a quite correct prediction. So you need to find alternatives to the least square. So the least square is simply a linear regression, no? So it's the first part of the linear regression, the least square. You do the square of the thing and you search for the minimum value, okay? When the number of predictor grows, you need a different procedure. And then the author of this book have proposed several alternatives, okay? This subset selection, which is the things that Michael was saying, which is best subset selection and stepwise selection. Those two things can be put in comparison. you can go through and see the differences within them, which is by talking about those things that will quite sound understandable, you know, like one both start with zero predictor, so you make a model with zero predictor, and then you add one predictor at the time. The difference between the two is that one multiplicates the number of predictors, so the number of predictor grows adding predictors, because it takes consideration of all combination of the variables, while the other one select a p minus k number of predictors, so the number of the possible models that will come out of this second method will be quite lower. So, and this is the stepwise selection. Then I don't know, we in the lab there is a data set, a baseball data set, which is used for with a specified package. So in practice, how do you make this subset selection? With a function. You use a function. There's a function you put inside your model fit, and it releases a certain value. So then you compare these values and select the different metrics and choose the lowest value for the R square or the highest value for the other ones. So the other two methods they suggest are the shrinkage and the dimension reduction. Okay, about what he was saying here, I don't know. Do you the things that I found interesting was that when you have performed the subset selection methods, which is best subset and the step selection, then for both method you need to after you have performed this selection, choose the optimal model, and for doing that you basically use other metrics. I don't know if you know this. Do you know this? For example, the CP, the AIC, and the BIC metrics, for example. I don't know. Do you use it? Do you use this type of metrics?
Because I encountered AIC and BIC in a time series course. And I remember a pretty elaborate explanation about why that was superior to, you know, RMSE or some of the others, especially in a time series context.
But because we usually talk about.
Yeah. There's an explanation here about the R squared cannot be used to select from among a set of models with different numbers of variables, so they're not comparable. and AIC is for some reason.
Okay.
And a similar experience, where it came up in the time series class that I had. It was kind of the same thing, like AIC is the way to go, and but yeah, I'm kind of new to using some of this in the real world, so but I've seen it in classes.
Okay. You muted, Michael. I don't know. Were you saying something?
No,
You're muted.
I'm done. Yeah.
No, I was saying we usually check for the R square, for the RS, so the residual sum of squares, at least are the things that are most sounded. Usually we at least for the book clubs follow it. This is the first book club which I found these 3 new metrics, which are not new to me, but you know, if you do not use it, they may be new. So in this context, they are they call up these 3 metrics as a further level of selection of your model. When you finally have, because this chapter is quite interesting. If we go through the lab, for example, we have this ITER data set, which is a baseball data set with data about baseball, and what we want is to predict the salary of the players. So he uses this LIPS package, which provides the function reg subset for making the subselection. Okay, so what I meant to say is that at the end, when you work, you apply a function which release certain numbers, and then you have a threshold to decide if your results are within this threshold, so if you accept the result or not. And here let's say that we are talking about baseball players, but we can talk about many other different things when in real world we are analyzing data that are with a high number of predictors. So after I have selected with this number of predictors, and we decide which one is the best composition for making our model. So my experience was that I needed to check for the correlation within the predictors and then decide which ones were more correlated and put them inside a model. Then run the model with a function, if it's a linear model, logistic model, whatever it is, and then consider the result of some metrics. So in this context, for example, the residual sum of square or the R square. Then here we have a larger number of predictors, so we need to select them and decide. So you have, I don't know, 1,000 number of predictors, a million number of predictors, like when you do real data, there would be different condition. No? So you can apply this subset selection and check the 2 classical metrics, but then you do a further check to see with this CP, IIC, and BIC if the number of predictors which select the best model changes. So you have a larger variety of metrics to apply to a certain number of models that you have made, shuffling the number of predictors. Okay, it's a sort of when you do cross validation, for example. No, you do cross validation. You do like shuffle your data to see if your prediction will change when you test within the training and the test set. Here, we still need to get there. So we are still at the correlation level. So we are still selecting the number of predictors to be being applied in our model. Okay. So we can use this other three metrics. I don't know if you want to go. You need to see how the metrics are made, or if you need to do this or not. But for example, you know that the residual sum of square is the sum of the residuals. Then there are a certain other number of metrics, which are the adjustments of the residual sum of square. So you do like apply a log of the number of predictors to the residual sum of square, and you have a new matrix. Then you can do a little slight modification of the residual sum of square, just as the same you have a modification of the R square. You have the adjusted R square and the R square. So these other metrics as you can see here, the BIC, DCP, and in this case have been considered just these two and not the AIC, because the result, the AIC, is exactly as the same as CP. So when these four are put in comparison, you can see that the number of predictors is quite the same, but is not exactly the same. So one matrix suggests you to select 10 predictors, another matrix suggests you to select 7 predictors. So what you should do, you need to run, you finally have a full test selection of your possible models with different number of predictors. So you, in this case, you have you can run and test the prediction on 7 predictions, on 10 prediction, on 11 prediction, to see which one within this composition releases the best result. For example, the CP, this technique, this metric is the CP, and it's an adjustment of the residual sum of square. So it's like an average of the number of observations, but then you add this little bit here, which is to the sigma squared, and you actually you are making an adjustment to the residual sum of square to obtain a new metric, where, for your curiosity, for example, it's the selected number of predictors, and then for example, within, when you use tidy models, for example, and then you can adjust the upper parameters when you make a model. For example, here is the case when you talk about the penalty. Okay, so you ask for an adjustment of the residual sum of square as a Furter matrix for a level up of selection of your models. Okay. I don't know. Then the EK information criteria, as I said, there is the same result as CP, so we don't mention it. And then there is this Bayesian information criterion, which is again an adjustment of the residual sum of square. So you do always the average, but then you add the log of the number of observation. So they are, I don't know if you're interested in these things, but they are slightly little modification that they change something, but not, but give you that flavor of difference within the things that makes you think, which and let you do a further selection of the selection. Okay, so I have 1,000 predictors. I run a stepwise selection, or so our techniques, one of the two techniques for selection. Then I obtain an average of 10 possible predictors, which there will be the best one for making my model. But then I'm not sure about that, so I want to be sure, and I apply this matrix, this other matrix, just as the same when I retrieve the residual sum of square or the R square, to have to obtain different numbers. So I obtain like 6 predictors are fine, 7 predictors are fine, 10 predictors are fine. So at the end, I have like 4 models with different number of predictors that I need to choose from. And this is a good result, because I started with 1,000 and I didn't know what to do. Or I started even with 20, just 20. But then if I do the number of predictor P, so like the permutation, no, all the possible combination of my predictors, I obtain a huge amount of predictors. So this way, at least I've obtained 4 possible models with 4 different number of predictors, but they just 4. Okay, so as I said, then having done that, you might not be enough satisfied, you know. And in my the authors suggest that in this condition you might want to apply cross validation on top of all of these things, because then you want to see how the thing goes if I shuffle these 4 models differently and see with cross validation how are my prediction. So the lab has used this function here, reg subset, which I've mentioned. And with this function, basically, if we can see what is said. This is from the lib package. You can do backward selection, forward selection, but then you can even do like here as an alternative. For example, we can estimate the test error. How do you estimate the test error? With the matrix, using the matrix, no? So the metrics that we have just mentioned. So as an alternative method, we can estimate the test error using a validation set and cross-validation method. So with the same function, you again run the this function is I'm doing things for granted because I've already done this bit. I don't know if you have seen the video, but this function is the same function that makes the model. So it's like LM function, okay? But in this case, it doesn't apply the model, it makes a selection of the predictors. And when I want to do the cross-validation, I still I divide my data set this time within training and test data set, and then run this function. So I make a training set and test set, and then run the function. What I retrieve are all the coefficients of my best of my my predictors. Okay. This time I've used all the predictors, but I have reduced the number of observations. And this is one more big key takeaway of the chapter, because there is a difference between when you have a certain number of observation, which is n, and a certain number of predictors, which is p. So if you have very few number of observation, it's difficult for you to run a model to obtain a correct result. When you may obtain a correct result on a validation on a training set, but then you don't have the same result on a testing set. So this, on the contrary, you may have a larger number of observation and few predictors, and so still there will be a problem. So you need, it's up to, so there is a criterion for deciding which is the best technique to use. But when you have a larger number of predictors and a larger number of observation, you need to make step-by-step selections. Okay, I don't know. Then, so in this case, with cross-validation, we have split the data and obtain a matrix, and we see that we want to see this result on a validation set. So this is not tidy model. So he used a base model for doing this thing, and it creates a loop for looking at the validation errors. Okay. And this is the mean square error. Do you have any, I don't know, questions? No? Okay, so we search for the minimum value of this mean square error, because now you may ask why we are now searching for a mean square error and not, we were searching for the residual sum of square. No, doesn't make confusion this to you. Why now we are talking about the mean square error and not about the other metrics? What is the difference between the residual sum of square and the mean square error? why we use this and not the other. I don't know. This is ridge regression. Okay, so I don't know. In basically we do this the difference between these two. I can't find that anymore. Where is it? Okay, so this is the residual sum of square. Okay, but the residual sum of square is the difference between these two. Okay, so the mean square error is the mean of the residuals of the sum of the square residuals. So we are doing now a check of the model of the result with the mean of the square residuals. And so we obtain a certain values, and we want from these values the minimum value. Okay, so did you want to say something maybe?
I think I follow, and the question you posed, that's valid.
So basically we calculate one standard error of the estimated test, mean square error for each model size. And then we select the smallest model for which the estimated test error is within one standard error of the lowest point on the curve. So I wanted to clarify this thing, maybe with your intervention. What do you think about those things? So what is why? So I know that cross validation is like I take part of my data set, okay, and repeat this data set with different composition. What do you know about that? I don't know.
So you have respective holdout pieces, and like K of 5, you've got 5 different examples of something held out. So when you train a model, you compare the held out to the model trained at those hyperparameters, or those and so
okay.
The stability of the model across the whole data set is represented by the 5 different error sets, is the way I understand it. And but they did note that in some ways that likely overstates the error you would see on a test set, or it could overstate. So it's a generous or a conservative understanding of and that might have to do then why they choose to use MSC as the difference between the predictor and because those those on cross-validation, because you're training the model, like on when k equals 5, you're training the model 5 times. You've got the same data point showing up 4 times in the training runs, and then a 5th time as an error run. So you've magnified the
okay. So now I don't have just one model, because I've cross-validated. So I have, like, if I do 10 folds, I repeat 10 times different types of composition of models. So then I do the mean of the residual sum of square. And search for the minimum value. Okay. So while other techniques are ridge regression and lasso, which are the shrinkage methods. Because what happens that now this techniques contains the coefficient estimates that shrink the coefficient estimates towards 0. So you now have a model, but you need to reduce this model as well as the result of the estimates. So to reduce the variance. For example, let's see this in practice. He uses this GLMNet package, and with the same data set. And for ridge regression, it's again very similar to least square. So it's an adjustment of the residual sum of square. So you now have this lambda times the sum of the coefficients. Okay, the coefficients estimate. This is the shrinkage penalty. So now here the challenge is to identify which one will be the best penalty to choose. You can tune it with tidy models, for example, and it will tune it for searching the best one, but he does something for tuning. So you need tune and he does by itself, but how? What's happened basically? This is so the tuning parameter is lambda, and this is to control the impact of these two terms. And he says that lambda equals to 0 is when the penalty has no effect. So the ridge regression will produce a least square estimates. So obviously, as you can see, if lambda will be equal to 0, this is just the residual sum of square. So you have no adjustment to the residual sum of square. Instead, when lambda is greater than 0, the impact up to infinity, the impact of the shrinkage penalty grows. So the ridge regression coefficients estimates will approach to 0. So you run your model, obtain some coefficients, and then with ridge regression, what's happened is that you choose a penalty, which is lambda, of a certain level greater than 0, in a way that to obtain a value which shrinkage the coefficients level to 0. For alpha correspond to ridge regression model fit, alpha equal to 0, alpha equal to 1 correspond. This is the argument that you put inside the function. So if you choose 0, you call for ridge regression. If you call 1, you call for lasso in the formula.
It's funny they didn't call it mixture.
Right.
Okay.
We nearly done 15 minutes. What else? So for example, here, he made a grid and then apply the glmnet function with alpha equal to 0. This is he's calling the ridge regression. And gives a certain number of value for lambda taken from the grid that he just made. So this is the same data set that the baseball data set. And in this case, the values of the estimates have reduced. But we do not have a comparison, but we might have a comparison with when lambda is, for example, of a certain value. We see that things change if we change the value of lambda. So for example, here, let's see if I go this way. Okay. Okay, so we see that the ridge regression result is slightly different, and this is for n equals to p for a simple coefficient estimate for a simple setting with n equals to p, for example. We see that there is a difference within the least square when the use of least square and the ridge regression, as well as with the use of least square and lasso. And these are the coefficient estimates, and these are the y, so the outcome, so the things that we want to, the value that we want to predict. And so we have this value of the coefficients and the predicted value. In our case, let's pretend that this is related to the salaries of the basketball players. So we have predicted this value, and this corresponds to a certain value of the coefficient estimate for a specified predictor. And this value is different if we use ridge or lasso regression when we apply the technique. So the the coefficients estimate changes. And this obviously influenced the result. So this is the things that I wanted to say. In the lab, there is one more like example. If we use cross-validation to choose tuning parameter lambda, for example, and we use this function, which is CV GLMnet, and this function is, I don't know, because I've this function uses it's for retrieving these things automatically in a way that you can see that the value of the mean square error on the logistic on the penalty basically changes, even if these 19 are the number of predictors. Anytime we change the value of the penalty, the mean square error changes. So at highest value of the penalty, we have an higher value for the mean square error. There is like this S shape. And while for the lasso is as well as the same, so it's growing. Okay, I don't know. We can see principal component analysis and regression maybe next week.
Okay.
Yeah.
Sounds good.
Okay. So I think it. Let's leave the things like this, and then we go back here next week. Start from here. Yeah.
Yeah. Thanks.
Okay.
Thank you.
Bye.
Have a good week.
You too. Bye.